Hello everyone, welcome to our discussion of section 7.1 where we will be talking about calculating area between curves. So we've learned quite a few integration techniques. Now when we take the area, we find the area between two curves, we simply either integrate over the x-axis, which is what we've been doing so far, or we will integrate over the y-axis. That depends pretty much on the shape of the area that we're calculating. Sometimes it makes it more suitable if we integrate two functions between along the y-axis, and sometimes it makes sense if we integrate along the x-axis. Now, as you can see on the screen, I've broken this up into two cases. Case one is when we integrate over the x-axis. So basically the picture that you see on the screen says it all. So if you have two curves, and I've identified those with the blue line on top called f of x, which is, let's say this curve is being generated by a function called f of x, and the curve g of x, and that's the red one here at the bottom, that let's say that curve has been generated by a function g of x. So if we have two functions such that they're continuous with no discontinuity in between, and if one curve is at the top at the top of the other one, in other words, notation-wise, we say if f of x is greater than or equal to g of x at every point along that continuous domain for the function over some interval, let's say a and b, a being this side and b being this point along the x-axis, then the area that is we call S, defined in between those two regions, can be found using this formula. So we integrate from A to B, and the function that is larger function, in this case f of x. Geometrically speaking, we're talking about the curve on top, and then that's f of x, and then we subtract the curve that's on the bottom. And then, of course, dx, I've highlighted this because this signifies that we're integrating these two functions, the difference between these two functions along the x-axis. Now, why do we subtract? Well, if we look back at the picture, what does integration of f of x from a to b does? What does it do? Well, what it does is it finds the area that it's between the x-axis and the blue curve. Now, that's not what we want, right? We need to subtract this piece that is outside of region S, which is really the area, the shaded area we'd like to calculate. So in order to subtract this area, this region below the curve g of x, we simply do a subtraction here because integration of g of x calculates that area that is below, between the x-axis and below that g of x curve, and which is exactly what we do not want, because we want the area captured between f of x and g of x in between, and that's the way to achieve that. Okay, and of course integration is happening along the x-axis, so we have d of x here. All right, so that's one case. Case two is, as I said earlier, when we want to integrate along the y-axis. So in which cases does this happen? Well, if we take a look at this picture, notice that in this case, we don't have a curve on top and a curve below it, but we have a curve on the left and we have a curve on the right. Now, if we integrate along the y-axis, between C and D, what we will find is the area, the entire area between the y-axis and this red curve. Of course, that includes the area that is not being shaded. So it includes this piece that we don't really want. We just want the area of this shaded area because it's between this curve, this blue curve, and the red one. So what do we do then? Well, just like before, when we integrated along the x-axis, in this case, all we have to do is subtract an integral of the function that represents this curve. So if that function is called g of y and this one is f of y, we simply say integral from c to d, right, along the y-axis, which is all of that area, and then subtract this piece by saying minus this curve, g of y, or xl for the left-hand curve. Okay, so when we do, notice that when we, let me bring back the previous slide, when we integrate along the x-axis, both functions must be written in terms of x. In other words, x should be the independent variable, and f of x and g of x, or y, would be the dependent variable. That's the normal, that's typically the type of function we've dealt with, right? But not the only kind of function. When we integrate along the y-axis, we have to be careful because both of these functions that generate these curves, these two curves, must be written such that x is written in terms of y. In other words, x becomes the dependent variable in this kind of integration, and y becomes the independent variable. Okay, and we'll see examples of that. But that, to summarize what I've just said, to summarize this statement plus this, what has been depicted in this figure, we have this formula. So remember that when we integrate along the x-axis, we take the top curve and subtract the function that represents the bottom curve from that, or f of x minus g of x, right? But when we are integrating along the y-axis, we take the curve, we take the function that represents the right-hand side curve and subtract from it the function that represents the left-hand curve. In other words, this is what you see. X for being the dependent variable for the function that generates the right-hand side curve, x of r minus x of l. And then dy, of course. All right, so that's how we do integration along the y-axis. So now let's look at a few examples of how we can achieve that. So in this series of examples, they're all alike. First thing we want to do is we want to sketch a graph of both functions between which we're trying to find the area. And then after that, we conduct the integration. So in the following examples that are coming up, first thing is we want to sketch the region enclosed by the given curves. Then decide whether to integrate with respect to x or y axis. And when we do integration with respect to x, of course, that's when we use dx, or y when we integrate along the y-axis, dy. And of course, at the end, we want to find the area of the region. Okay, so the first example is as follows. We are given these two functions, y equals e to the x power, and another one, y equals x squared minus 1, x equals -1, and x equals 1. Notice these two pieces of information imply, they're kind of a hint that we need to integrate along the x-axis. And you'll see it better, if not already, after I draw a picture of these. And that's the first thing they ask us to do. In the following examples, sketch the region enclosed by the given curves. So let's do that. Okay, so all of these functions we're pretty familiar with going back to basic algebra, Math 126 and Math 127, if you've taken those classes here. That's basically the natural exponential function. This is the one of the more basic quadratic functions, and these are just two vertical lines, so we can easily draw these. So I'm just going to first draw the natural exponential function. It's going to go something like this. Like that. And so this is y equals e to the x. Then let me also, and by the way, this point is the y-intercept for this function, right? So simply, if you substitute for x with 0, we will get y equals 1, right? E to the 0 power is just 1. So that's 0, 1 point. And then for this case, this is simply a quadratic function that starts at origin but -1. So it's moved, going back to transformation of functions that we looked at in Math 126, this is simply x squared, y equals x squared function moved 1 unit along the y-axis. So let's do that. So if that's 1, then I want to stay to the same scale as much as possible. So somewhere here, we will have the vertex of that quadratic function. And what about the x-intercepts? So for x-intercepts, we will set y equals to 0, right? So we can do that very quickly here. We say 0 equals x squared minus 1. Do the algebra on this, what do you get? You get x equals, solving for x, you get x equals plus or minus 1, right? So the x-intercepts then are 1, 0 for the quadratic function, right? And then -1, 0. So that would be, if we take -1 as this, and 1 as this, I'm sure my drawing is off scale, but I'm doing the best I can here to keep things proportional. So then, if I draw let's see, if I draw a quadratic curve through this, we will have, let me draw it with this, going through that, and then this, and then this, and then all the way like that. Okay, so it's a little bit, I could have done a better job up here, but something like that. At some point they will intersect, the exponential function and the quadratic function. And then of course we have these two vertical lines. Let me also draw those so one is going through x equals -1, the other one through x equals 1. So let's do that. And so we have, I'm just going to draw a dashed line here, hoping to prevent this drawing to be too crowded. Like that. So this vertical line is simply x equals -1, and this one is x equals 1, right? And of course, we're looking for, the area we're looking to calculate is between all these elements, all these functions. So let me try to, then that would be below that. And here, to the right of this dashed line, and to the left of this one. And so that is the highlighted region, is what we're trying to calculate. Okay, I think like that, all the way to that corner. Okay, so now we know that if looking at this region, it's easy to see that we're integrating from that -1 to 1, where the top function is y equals e to the x, and the bottom function is the quadratic, well, I need to label that too, y equals x squared minus 1. Okay, so it's clear what the limits of integration should be, it's clear what the top function is, and it's clear what the bottom function is, and we're integrating along the x-axis. So let's do that. Okay, so we will say the area is equal to integral from -1 to 1, right? And the top function, e to the x, minus the bottom function, which is that, x squared minus 1, right? X squared minus 1. And of course, let me enclose these in bracket, dx. So this is pretty critical to note from this point forward in this course, that we have to be mindful about when we integrate, which axis is it with respect to. Okay, in this case, with respect to the x-axis. All these functions are easy functions to integrate when we compare them with the functions we've been integrating lately. So, but let me distribute this minus into this function. So what do we get? We get minus x squared plus 1 dx, right? And so let's integrate. We will have the area is equal to e to the x is the integral of itself. So you integrate this, you get itself, and minus 1/3 x cubed plus x, of course, going from -1 to 1. By the way, that property of integrals that you can use is that, well, in this case, can we do that? No, no. In this case, we couldn't do that. So sometimes, if you have a graph that is symmetric, if you have an even graph, right? If you have an even graph, and then from -1 to 1, then, or even function, and then you have some kind of a symmetry going about the y-axis, then you can change this to 2 times and then change the limits of integration from 0 to 1 rather than negative 1 to 1. That would be an option if we had symmetry. But in this case, I'm just going to go ahead and keep everything, the limits of integration as they are. And then, so let's evaluate this function or this expression. We have, let's substitute for x with 1 first. So we have e to the 1 is just e minus 1/3 plus 1 minus e to minus 1 power, right? When we substitute for x with negative 1. And then here, minus 1 cubed is minus 1 times minus 1/3. We get plus 1/3 and plus minus 1 or minus 1. Okay, so if we distribute this minus into this, these elements, into these terms, what do we get? We get e, this one stays the same, all the terms here, and then we end up with minus. Let's rewrite this with positive power, so 1 over e, minus times 1/3 minus 1/3 minus times minus 1 plus 1. If you do all the algebra here, this is the expression you should get. Please don't take my word for it, and see if you get this. If you do this on your own, and you should get e minus 1 over e plus 4 over 3. Okay, so notice that in this case, I have basically kept all the terms in exact form. If, however, they ask us to calculate this quantity to certain decimal places, then we would do that. We would calculate e and then minus 1 over e plus 4/3 and round to certain decimal place. But in this case, as long as we're not asked to do that, I'd rather leave the answer in exact form. Okay, so that's one example. Let's do another example. And so suppose we want to find the region in between these two curves. So x equals 1 minus y squared and x equals y squared minus 1. Notice in this case that the x has been given in terms of y, right? And this is kind of a hint that maybe it would be a good idea, it'll be a good idea if we integrate along the y-axis for this one. We can always switch. We can always switch to solve these equations for y, and then we will have functions that y functions that are in terms of x, and then we can integrate along the x-axis. But before that, let's sketch both of these curves. Okay, so these are both parabolas, and parabolas that open horizontally, right? This we learned from the Math 127 course, or Trigonometry Pre-Calculus 2 course. We have y squared, and then x is linear, so we have parabolas that open horizontally. All right, so now if we draw this, we will get so let's find out the x-intercepts for this one. For this one, we will have, the x-intercepts, do I want to write it here? So let me write it here, actually. It's a good idea to put it here. So we have x equals 1 minus y squared. I strongly recommend that you pause the video at this point. I know we just introduced this topic. You've just seen one example, but it's worth to try to for you to pause the video and find the area between these two curves, and then unpause the video and see and compare your solution with this. Don't waste your time more than 15 minutes, but give it your own thinking first before you see this solution. Okay. So finding the x-axis or x-intercepts for this, that would mean if we substitute for y with 0, what do we get? We get x equals 1, right? So we have 1 comma 0 as the x-intercept. And that would be, let me take the increment somewhere here, like that. So let's say that's 1, or 1 comma 0. Okay, so for this function, so we did that, we found the x-intercept for this. How about this function? Let's do that here again. So for x equals y squared minus 1, the x-intercept, if we substitute for y with 0, we get x equals negative 1. So negative 1 comma 0. So let's put a dot here. And we know these are parabolas. We know they're open horizontally. So we know pretty much this one is going like that. That one is going like that. Okay. Now we can find out what the y-intercepts are, right? Let's do that. So to find the y-intercept for this function, simply we can substitute for x with 0 and then solve for the y values. So 0, that would be, so if you do that, I'm trying to save a little bit space here, but so let's, for the y-intercepts, y would be 0. No, sorry, so for the y-intercept, so x would be 0, and then solve for y. Y squared equals 1, which means y equals plus or minus 1, right? So let me correct that by saying plus or minus 1. Plus or minus 1, and that's like that. That in the parentheses. Okay? So that means that we should put, let's put 1 dot here for 0 comma 1, and 1 dot here. I'm trying to scale these so they're equal. And that one 0 comma negative 1. Okay. So for this point, let's draw that curve. And so this one would be, and that is that one. So we know that the curve should go, the line comes through here, then passes through that vertex, and then curves back this way and goes that way. Okay. I'm sure my drawing is not as good as what a computer could do, but you're welcome to use your calculator or computer, Desmos.com. If you don't, I'm sure you know that, but Desmos.com, for those of you who have not visited that website, helps you graph these type of functions and does a pretty good job. So for the other one, and let me label that, by the way, so this would be x equals 1 minus y2. Okay, so that's that. So let's graph this one. We already know what the x-intercept is. To find the y-intercept, let's, so we substitute for x with 0. Once again, when you solve for y, you get plus or minus 1, right? For this function as well. So this function is opening to the right, and it's going through the same y-intercepts as the other curve. Okay, so let me also draw that like that and like that. Okay. So it's now clear that the area that we need to calculate between these two regions is this area. Okay. All right, great. So these two functions, both of them are x. X has been given in terms of y, right? X given in terms of y. So it's okay. In this case, if we wanted to integrate along the x-axis, we could. If we want to integrate along the y-axis, we can. And we have, but I'd rather keep the integration along the y-axis because we have a right curve and a left curve, and so that in itself, and the fact the functions are given, each function is x given in terms of y, so that all is in agreement that we should use integration along the y-axis. So let's do that. So, and the right curve, remember that the right curve minus the left curve. Okay, so, and by the way, let me also label this curve. So this will be x equals y squared minus 1. Okay, so we have, and we know the limits of integration for along the y-axis. It would be from -1 to 1, right? Look at the y values here, and from -1 to 1, from here up. Okay, all right. So we have A, or the area, equals integration from -1 to 1. The right curve is this one, 1 minus y squared. 1 minus y squared minus the left curve, that one, which is x equals y squared minus 1. Y squared minus 1. Let me enclose these inside a bracket here. And of course, dy. And this is pretty important that we're now integrating with respect to y. Okay, so going through this, let me distribute this and simplify this inside the integrand a little bit. So -1 to 1, and then we have 1 minus y squared minus y squared, distributing this, plus 1 dy, right? So we end up with a equals that integral, and we have 2 minus 2y squared. Of course, we can factor out the 2. So we can say 2 times -1 to 1, and then y minus y squared, 1 minus, yeah, that's correct, dy. And then let's integrate. We have 2 on the outside here, let's not forget that. And then y, integral of 1 is y, minus 1/3 y cubed from -1 to 1. Okay, so if I come up here for the rest of this, maybe to this point, right, like that. Okay, so we have a, I want to start here, a equals, let's substitute, we have replacing y with 1, so we have 1 minus 1/3 minus, now replace y with minus 1, minus 1 minus 1 cubed is minus 1 times minus 1/3 plus 1/3. And then a would be equal, so let me not forget that the whole thing is being multiplied by 2, so I'm going to put the 2 here, and I'm going to put the bracket here. And then also, so let's simplify the inside. So we have 1 minus 1/3 plus 1 minus 1/3, and then a equals 2 times. If we add all of this, we will get 4/3, and then we should get a equals 8/3. Okay, so that's the area of that region. All right, so let's do another example. So suppose we want to find the area between these curves, y equals e to the x and y equals x times e to the x, and then we want to start from x equals 0, right? So this is just an indication that we want to stay on the positive side of the x-axis. X equals 0. We'll start from that, but of course we can't stop there because otherwise the area would be 0. So we should have some point of intersection between these two curves. Let's draw the curve. Okay, so this function e to the x, we can start it from here. We've drawn exponential function plenty of times in basic algebra classes, so we know that it goes something like this. It starts here, crosses the y-axis like that, and then steeply goes up like that. And then, so this is y equals e to the x. And then this one, it's very similar to this, but it's going to go through the origin, right? Because if x is 0, then y would be 0. Here, if x is 0, what do we get? We get the y-intercept. As a matter of fact, let's label it. So that's just 0, 1, right? For x 0, y would be 1. Now this one, it's going to go through the origin because if you substitute for x with 0, you get 0 because of this multiplier. So, but it's going to behave the same way as y equals e to the x, except it's going to go through the origin, and except it's going to go faster. It's going to grow faster because of this multiplier when it's positive. So I'm going to draw it from here. Hopefully I can do a decent job. So it's going to come here, go through the origin, and then do that, and continue on. So at this point, they're intersecting, these two curves, right there. And we are told that the initial point, this is just the initial point, we want to start at x equals 0. So if I was to highlight this region for which we want to calculate the area, it would be this region right there. This tiny little region. Right, that's the region we're calculating the area for. Okay. All right. So we already know that's 0, 1. And we also want to find out what that point is, right? Because the integral, it's going to be along the x-axis, and it's going to start from x equals 0 to x equals something. What is that something? We need to find that out. Okay? We need to, let me drop a dashed line here and here. Okay? So that because that point is the point of intersection between these two curves, we can easily set them equal to each other. So let's say, oh, by the way, let me label this before I forget. So that curve is y equals x times e to the x. Okay, so let's set them equal to each other. E to the x equals x times e to the x. Let's move both to one side. So we get x times e to the x minus e to the x equals 0. If we factor e to the x out, we get x minus 1 equals 0. Notice that for this equation to be true, either this factor has to be true, or it has to be equal to 0, or this factor has to be equal to 0, right? Now, this factor, it's going to, for negative values, it'll be very small, but we have all positive quantities here. So this factor is never going to be 0. So for this equation to be true, this factor has to be 0, right? Okay, so from here we say x minus 1 equals to 0, so x should be equal to 1. And if x equals to 1, that means y has to be equal to e, right? You can just try that, substitute for x with 1. From both equations, you're going to get e, and you should get that because at that point of intersection is common to both functions. So then the function value y is e, and it's going to happen when x equals 1. Okay, so that question mark that I wrote then is 1 comma e. Okay, so then we now know from where to where we should integrate. We're going to integrate from 0, x equals 0, to x equals 1. And the top curve is e to the x. The bottom curve is x times e to the x. Okay, so let's do that. So we have the area is from 0 to 1, e to the x minus x e to the x. And of course, this is the dx with respect, integrating with respect to the x-axis, or with respect to x. Okay, so we've done, this is the first term here is easily integrated. The second term, we've integrated this term before in the previous section, and we know from the previous sections we have to use the integration by parts. So let's do that. So using integration by parts, for that one, just for this term, we have, let's set u equals to x, and that means that du is going to be dx, and then dv, let's take that as, since u is x, then dv is going to be ex dx, right? Ex dx, that's the only thing left. U is already been set equal to x, so e to the x times dx, it's going to be our dv, which means v, it's going to be e to the x. Okay, so now we know by integration by parts, this should be uv minus integral from 0 to 1 of v du, right? V du. Okay, so we're going to, so once we figure this out, I'm going to replace it in here. And so that will be just the components of that piece. So uv would be x times e to the x, and then of course going from 0 to 1 minus integral from 0 to 1 of v du, so e to the x dx. Okay, so now let's rewrite, after doing all this work for integration by parts, let's rewrite this integral in the new way. So we're going to write this as, we're going to separate them. We're going to separate this and say 0 to 1 e to the x dx minus all of this. So minus x times e to the x from 0 to 1 minus, as I do this, I'm going to distribute this minus into both these terms. So that is now minus, and now that minus times this minus is going to give us positive integral from 0 to 1 e to the x dx. Okay, so this one is easy, e to the x from 0 to 1. This one we can calculate, I guess. Well, let's do that in the next step. So minus, again, x times e to the x 0 to 1. And this one also, it's easy. We have e to the x going from 0 to 1. Okay, so now we can plug in. So that will be plugging for x with 1. We get e. And then plug in for x with 0, we get e to the 0 is 1, so minus 1, right? That's just that. Then minus, then let's calculate this piece. We have 1 times e to the 1, it's just e. And then minus, substituting for x with 0, we get 0. And then plus this piece, we get e to the 0 is 1, like that. Okay. All right. So what do we get? We get, let me bring this down a little bit. A equals e minus 1 minus e plus e minus 1. And so we get this e and this e cancel each other out, these two. What do we get? We get e minus 1, they add up to minus 2. So the area, the final result, is e minus 2. Again, as before, I'm going to keep this in exact form. I'm not going to calculate the decimal value for that. Okay. Unless the question asks me specifically to do that. All right, so let's do another example. So suppose we want to, please make sure that you pause the video. You've seen plenty of examples now, and it's a very good idea that you pause and do your own work and then come back to this video after you've finished your own thinking. Okay. All right. So both of these functions are very familiar to us, right? This is the absolute value function. This is the quadratic function. Now, the absolute value function, of course, and I'm going to sketch the graph for both of these first, but well, let's do that actually. Let's draw the graph first, and then we'll do the calculations. So we have this, and then we have this. We have y. And so let's increment this. Well, so the absolute value function, we know it looks like a V shape. So let's draw that. Like that. And then also on this side. And then the quadratic function is simply the basic y equals x squared function moved down 2 units. Right, so if we want to do that, I guess we can do that here and then here. I'm trying to draw these as much as possible to scale, so -2, and then one and 2. I don't know how good this will look at the end, but I'm trying to make these increments as equal as possible. So 1, 2, -1, -2. Okay, so the x-intercepts for this quadratic function, we can set the y equals to 0. We get x squared minus 2, and then so x would be equal to plus or minus square root of 2, right? So we'll have the square root of 2 comma 0, and then minus square root of 2 comma 0 as well, like that. Okay, so that would be somewhere between 1.4, right? It is this irrational number around 1.414. So let's say 1.4. So that would be, so the x-intercepts would be here. Let's say somewhere here, and then also on this side, somewhere here, roughly. Okay. And then, so these, let's see, so how do we, and now at some point they will intersect this. Again, I don't know how good this graph will look at the end, but to draw it as best as I can, then let me see. Let's figure out at which point this curve and that one intersect. So let's do that. So using the definition of absolute value, what do we have? We have y equals absolute value of x equals x if x is of course greater than or equal to 0, minus x if x is less than 0, right? We learned this back in pre-calculus. Now let's set each one x equals to that, and then minus x equals to that, to figure out at which 2 points the quadratic equation intersects this absolute value function. Okay, so one time we should set x equals that, and then minus x equals that. Let's do that. So we have, let me do that here, or yeah, I guess we can do it here, right here. So if x is greater than or equal to 0, then we have x equals x squared minus 2. And then this is a simple quadratic equation, so we have x squared minus x minus 2 equals 0, which can be factored into x minus 2 times x plus 1 equals 0. Now, from this, let's set each factor equal to 0 and solve for it, for x. So x minus 2 equals 0, therefore x equals 2. And from here, x plus 1 equals 0, so x equals minus 1. So because this left-hand side is coming from an absolute value function, and for this one we're analyzing when x is greater than or equal to 0, so we cannot accept this answer, right? Because this is telling us this is our condition. As we solve this quadratic equation, this was our condition. So we can't have x and negative values. So this one is out of the question. It's this one that we accept. This is the one we accept. And so That point of intersection then would be it would happen at x equals 2. So if you plug in for x equals 2 in either equation, what do you get? We get y equals 2 here, and y equals 2 here as well, right? 2 squared is 4, minus 2 is 2, so y equals 2. So the point of intersection for the curves, and for this and the one that I will draw, it's going to be 2, 2. Okay? Now, let's do the same analysis this time when from the absolute value function we're going to take negative x, not x. We've already finished with this analysis. Let's analyze this one. So if, we're going to say if x equals less than 0, which means we're going to use this piece of that function and set it equal to that function. Okay, so if x is less than 0, then we have negative x coming from the absolute value function equals to the same quadratic expression. So once again, we solve this, x squared, move everything to one side, and we have plus x minus 2 equals 0, and then x plus 2 times x minus 1 equals 0. That's just a factorization of that. I think that would be correct. And then, so if we once again set this piece to equal to 0 and solve for x, we will get x equals negative 2, right? If we set this one equal to 0 and solve for x, we get x equals 1. Now, which one of these answers is acceptable? This one, right? Because the condition for this equation to be true, since we took negative x from the absolute value function, is that x has to be less than 0. X has to be some negative value. So this can fit the bill, right? This is out of the question. So this is the one that is acceptable. It's less than 0. So then from here we have negative 2, and then of course if you plug in negative 2 for x in either of these functions, what do we get? From here we get 2 again, y equals 2, minus 2 squared is positive 4, minus 2 again positive 2 from that equation. So minus 2 comma 2 is the intersection point on the other side of the graph. Now we have a pretty good idea where these points are. So, I mean, the points of intersection between the quadratic function and the absolute value function. So that would be negative 2 and 2. So that would have to be here somewhere. And then 2 and 2. Well, I want these to be equal or at the same, so that should be here, somewhere here and here. I know my drawing is off, but at least if it's half good, it's not too bad. And of course, the y-intercept here is x 0 comma negative 2, right? Just plug in for x with 0, y would be equal to negative 2, so we're here. For the quadratic function, we are here, right? We're here. All right, so now I will try as best as I can to draw a curve through these points. All right, like this. Oops, I missed that point. Sorry about that, but this line should go through that. And then it should go through this one, which I had already plotted like this and like that. Okay. All right. So you can see, even though my drawing is not that great, but there is a symmetry going on here, right? So we will take advantage of that later when we start to integrate. And so now we know what these points are. That point is 2 comma 2, and that point is negative 2 comma 2. And let's integrate along the x-axis. It would make great sense to do that. And then, so our integral should go from negative 2 along the x-axis to positive 2 along the x-axis. Okay, and let me shade this area in between these two curves. And there's also no debating between which curve is the top curve and which one is the bottom, right? We can easily see that relationship, the absolute value function being the top curve. Oops, I don't like it when it smears on the paper, but it does it since we're dealing with really wet ink here on the page, like that. Okay, so, and I should label these. That curve is simply y equals x squared minus 2, and that curve is y equals absolute value of x. All right, so let's do the integration. Integral from negative 2 to 2, the top curve is the absolute value function, the bottom curve is the quadratic one. So we have the absolute value of x minus x squared minus 2 dx, right? Now, the fact that this area we're calculating is symmetric with respect to the y-axis makes it possible. So this is, we can use that property of integrals and take this integral from 0 to 2 and then put this 2 in front, right? We double that quantity times integral from 0 to 2, no longer from negative 2 to 2, but this 2 twice that, right? This is a property of integrals that we studied earlier. And so when we do that, then it's not necessary to keep the absolute value around x. We can just say x, because everything is going to be positive in this interval, 0 to 2. And then minus x squared minus 2 dx, right? Again, this is very important to make notice of, or to notice that we're integrating along the x-axis. All right, so let me distribute this negative and then carry out the integration. A equals twice integral from 0 to 2 of x, distribute this minus x squared, minus times minus positive 2 dx. And then, of course, we have a equals twice. Integrate this expression, we have 1/2 x squared minus 1/3 x cubed plus 2x from 0 to 2. Okay, like that. Okay, so let me come up here. Put the rest of the solution here. So we have a equals, let's substitute for x with 2. So what do we get? We get 2 squared is 4, 4 divided by 2 is 2, 2 cubed is 8, minus 8/3, right? Minus 8/3. 2 times 2 is 4. And then, of course, if you replace x with 0 in all of these, you get 0. So that minus 0. And of course, let me not forget that there is a 2 in front here. There's a 2 here. There's a 2 here, and which I have to also put here, right? I'll just put it in red so it sticks out. Okay. All right. So after we do the, of course, common denominator and do the algebra, so we should get 20 over 3. Okay, so this is, since my red line or red ink inadvertently went through it, let me correct it with that. 20 over 3. Okay, so that's that. Let's do one more example, but this example, it's going to be a little bit different than these, which is good. We need to learn new techniques with each section, so that's, and it's different than the cases that we've seen, examples we've seen so far. So we want to find the area between these curves, 1 over x, y equals x, y equals 1 over 4 times x, and the condition is that x has to be greater than 0. Okay, of course that's clear. Why? Because we have x here in the denominator. Okay, just like before, let's draw the graph for this scenario. So 1 over x, we know from the past that this is a graph that, this is a rational function graph that has 2 pieces. One piece ends up here in the first quadrant, another piece ends up in the third quadrant here. But in this example, we really have no need for the piece of this graph, of this function, that ends up in the third quadrant, because in that quadrant x values are negative, and we don't need that. We are only focusing on the section, area section for x values greater than 0. So all I'm going to do is I'm going to draw this piece, the piece that is in the first quadrant. So if I do that, I will get, well, let me use my red ink here. So something like that. So this is y equals 1 over x, of course just the piece for which x is greater than 0. All right, so y equals x is just a straight line that dissects that quadrant, right? Again, I'm going to draw the piece of it. Maybe I'll draw a dashed piece here, but we only need the piece that is in the first quadrant for which x values are positive. So I'm going to, that line should dissect. I'll try to, maybe that over here, like that, and maybe a little bit dashed here for that. Right, so this is y equals x, and this one is also a straight line that goes through the origin, but it's a much more flat line than y equals x, and you can clearly get a sense of that, because if x is 4, y equals 1, right? 4 times 1/4, y is 1. If x is 12, y is equal to 3. If x equals 16, y equals 4. So x values are much larger than the y values, which indicates this line is really flat. It's it goes like this, right? So let's see. So if we, I think that would be a good position for that line. So again, I'm going to draw the positive side with a dashed extension to it on this side, and this is y equals 1/4 x. Okay. All right. So now it's clear where this area is that we're looking for. It's enclosed by all these curves for which x values are all positive, right? Again, my marker is smearing a little bit. Sorry for that, but you can see where I mean to highlight, right? That region, all of that. Okay, so now we need to, here's the thing. So now what do? Because we start from here, which is 0, 0, that point. And then we have this point of intersection. Let's call it A. And then we have another point of intersection here, and that is B. Let's call it B. Point A and point B. Now, if we integrate from here to here, the top curve, it's going to be y equals x, the bottom curve up to this point, it's going to be y equals 1/4 times x. But after point A, the top curve changes. It changes to y equals 1/x, and then the bottom curve stays at y equals 1/4 times x. So the bottom curve stays the same throughout this integration that we're constructing, but the top curve doesn't stay the same. So what do we do next then? Well, when we have different curves, changing like this, then we find what point A is, we integrate from 0 to that point, with the top curve being y equals x, the bottom curve being 1/4 times x, and then beyond point A to point B, then we add another integral from 1 to 2, and you'll see from 1 to the next point, B, for when the top curve is y equals 1/x, the bottom curve is 1/4 times x. Okay, but the first order of business is we need to find the coordinates of A and coordinates of B, because we need the x components there. Okay, that determines from where to where we should integrate with these two curves and these two curves from that point forward. So let's find what the coordinates of A and B are. Okay, so A, and we've learned how to solve systems, right? Because A is the intersection of these two lines and B is the intersection of these lines, so we can easily make use of systems to get what we want here. So A, system A, as you can see on the screen, it's going to entail this line, y equals x, and this curve, that's the intersection of this curve and that line. So y equals 1/x. Point B is the result of the intersection of these two curves. One is y equals 1/4 times x, and the other one is the y equals 1/x, right? Okay, so let's solve for x and y in each system, and that'll give us the coordinates of A and B. Okay, so here we'll set x, the left side are equal, so the right sides must be equal. X equals 1/x. Multiply both sides by x to get rid of this fraction. We end up with x squared equals 1, which of course means x equals plus or minus 1. Okay, so which one of these is acceptable? Of course, the -1 has to be tossed out because from the get-go we have this condition that x has to be some positive value, non-zero positive value, right? So only x equals 1 is acceptable. Now, if you substitute that in these equations, what do you get? In these two equations, which form this intersection, these two lines, you get y equals 1, right? So the point of A, and so let's say A is the point A coordinates are 1, 1. Okay, so that's point A, like that. So that point is 1, 1. Now, how about B? So let's solve this system. So we have the left sides are equal, so the right sides must be equal as well. So 1 over 4 times x equals 1 over x. So if we cross multiply, what do we get? We get x squared equals 4. Therefore, x equals plus or minus 2. So which one is acceptable? Of course, only the positive one, right? Because, again, of that condition, x has to be positive. So we write only x equals 2 is acceptable. Okay, so coordinates of B then is when we plug in in this system, when we plug in for x with 2, what do we get? We get 1/2. Y is 1/2, right, in both of these. So B has coordinates 2, 1/2. Okay. Now it's really easy to see what's going on here because A, that would be 1, 1, so it means that is 1, and B is 2, 1/2, so that point is 2. So now our integrals will be integral of this top curve and this bottom curve, the difference between this top curve and this bottom curve from 0 to 1, and then integral from 1 to 2 of this top curve and this bottom curve. Okay, so we're going to set it up like that. So we have the area is equal to integral from 0 to 1 of x minus 1 x minus 1 over 4 times x, right? That's the bottom curve. Dx plus, right? The integral that I just wrote, this takes care of this piece, this area, from 0 to 1. Now from 1 to 2, the top curve changes, so we go 1 over x minus 1 over 4 times x, right? This is the top curve, this is the bottom curve. So 1 over x minus 1 over 4x integrated from 1 to 2. So let's add that. Integral from 1 to 2, right? From 0 to 1 and then 1 to 2 of 1 over x minus 1 over 4 times x dx. Okay, so now we're set to calculate. To do the rest is just easy integration and basic algebra. So A would be equal to 1/2 x squared minus 1 over 8 x squared. And then, of course, this is going from 0 to 1 plus, this is 1 over x, so the integral of this is natural log of absolute value of x. We don't need the absolute value because from 1 to 2, x values are And of course, I have to highlight that we're integrating with respect to x-axis, or the x variable, I should say. So because in this range, in this domain, x values are positive, I just write natural log of x minus 1 over 8 x squared, going from 1 to 2, right? Okay, so then after that, we'll just plug in. So we have 1/2, substituting for x with 1, 1/2 minus 1 over 8, and then if you substitute for x with 0, you will get minus 0, like that, and then of course plus natural log of x, so that would be natural log of 2, natural log of 2. 2 squared is 4, divided or times minus 1/8, that's minus 1/2, minus natural log of 1, of course we know that's 0, and then minus 1 over 8, right? So what do we get? Let's distribute all of this and then simplify. So we get 1/2 minus 1/8 plus natural log of 2 minus 1/2. Look at these are simplifying already, right? Minus 1/2 and positive 1/2 add up to 0. So, well, let's continue, but minus natural log of 1 is 0, minus times minus is positive 1 over 8. Okay, so as you can see, 1/2 and negative 1/2 add up to 0. Negative 1/8 plus 1/8 add up to 0. And we just end up with natural log of 2. So that area is equal to natural log of 2. So that's the area formed by all these three curves, such that in the middle we had to change the top curve from one to the other one. Well, I hope this video session was helpful, and we will do more examples in class. Altogether, you should have about a dozen more examples between this video and the examples you'll see in class. Add to that maybe half a dozen examples, or just about that number, are solved inside your book, so you have about 18 examples. Please make sure whether you watch the video or you rewatch it, or you because I'm going to post these on Canvas, so make sure that you don't look at these solutions. You have your own stack of scratch paper, you solve these, and then you compare your solutions with either these or the ones that your book solves, and I'm sure you will progress very fast and very well. And thank you for watching this video until this point. For now, have a nice day, and I'll see you again next time.